Welcome back, everyone. Well, I hope your heads didn't explode from all that excitement. And if not, that's good because we'll need to harness it to learn about correlated groups t-tests today. So my name's Rob, and this is the first part in a two-part lecture on correlated groups t-tests and confidence intervals. So in this first part, we're going to we'll start looking at the distinctions between different types of research designs. And then we will talk about the nature of a correlated groups t-test. And then we'll work through an example together. As always, over here are the PowerPoint slides. And then up here is our virtual whiteboard. And we'll use the whiteboard to do hand calculations and show tables and various things like this. So if you have any questions, don't hesitate to leave a comment in the comment section. And if you find this video helpful, don't forget to smash that like button and hit the notification bell to receive updates on new videos just like this one. Okay, so, I forgot. In the second lecture, we're going to be exploring confidence intervals, what they mean, why they're important, how to compute them, and how to report confidence intervals in APA style to help your reader understand your results a little more clearly. So why don't we just dive in and let's talk about, what is a t-test in general, right? So we've been doing z-tests, we've been doing t-tests. There's a lot of different types of t-tests. Well, a z-test, we're comparing a population mean when we know the population standard deviation to a sample mean. And we get into t-test territory when we no longer know what the population standard deviation is. And we have to estimate the population standard deviation from the sample standard deviation. Now, why are we estimating standard deviations? Well, a standard deviation is a biased estimate of a population standard deviation. So we have to make some adjustments. However, a sample mean is an unbiased estimator of a population mean. So in other words, a sample mean is our best guess about the population mean. Okay, so we conduct a t-test when we need to estimate a population standard deviation. Now, we've conducted one sample t-tests in the last lecture, and today we're going to be moving into correlated groups t-test territory. So what is the distinction? Well, that's a great question. Mathematically, very, very little difference. In fact, the t equation for a correlated groups t-test is exactly the same as for a one sample t-test. The difference is in the design, right? So a correlated groups t-test, we have what we call a within subjects design. And that means that we measure some person at time 1, and then we measure them again at time 2. Now, it doesn't necessarily have to be time. For example, I could capture, if I put an EEG cap on someone's head, I could capture a repeated measure or a within subjects measure and compare different electrodes that occur at the same time. But they're within the same person, and that is the critical thing. The way you determine that you're going to be conducting a correlated groups t-test is when you know that each participant gets both levels of the IV. So essentially, a correlated groups t-test asks the question, did the mean of the sample change when comparing pre-test to post-test scores? Or even more specifically, does the difference between two repeated measures of the same people change relative to a mean of no change or 0? So Basically, in order to do a correlated groups t-test, you need two means, one pre, one post, and the corresponding standard deviations from both measurements. So let's take a look at these equations, right? So essentially what we've been doing, and realistically what we're going to do for the remainder of this course, is we're going to be in the business of more efficiently computing error. So every test that we will conduct in this class is simply a difference over error. Sometimes that could be framed in terms of variance, like variance unexplained and variance explained. In the t-test arena, we're looking at the difference between two means, a mean difference, in units of error. And so let's look down at this one sample z-test equation. We can see we've got x bar, the sample mean, minus mu, the population mean, over the population standard deviation divided by the square root of n. Okay, so now let's look at the one sample t-test. Well, the numerator's the same, and now in the denominator all we're doing is replacing that population standard deviation with the sample standard deviation. And when we go over to the correlated groups t-test, we have the mean of the difference between time 1 and time 2 minus a hypothesized mean difference of 0. So our null hypothesis is going to be that there's no difference, right? And so that means we're just comparing the difference between time 1 and time 2 to 0, no difference. And then we divide by the standard deviation of the difference scores divided by the square root of n. It's exactly the same equation. We're just plugging in slightly different numbers based on our research design. So let's talk a little bit about two different types of research designs that we're going to encounter in this class. The first is called a between subjects research design. This is what I think most people think about when they think about how to do an experiment, right? And this is the case where each participant only receives one level of the independent variable. So you might randomly select people and then randomly assign them to some treatment group and then randomly assign the others to some placebo or control group. And then you give them the treatment and you measure them and compare those two groups. Importantly, those two groups contain different people. The groups are independent of each other. And in this case, we are going to use an independent groups t-test. So basically, the way this works is we rely on random selection and random assignment to make it a fair assumption that at the beginning of the experiment, both groups are equal. Because, the likelihood that you're going to find a tall person in group 1 is equivalent to the likelihood that you're going to find a tall person in group 2. And the likelihood that you're going to find someone who's extremely depressed in group 1 is the likelihood you're going to find someone extremely depressed in group 2. So all of these kind of individual differences are intended to be controlled for through random selection and assignment. Okay, so again, an independent groups t-test is a between subjects. It addresses a question that is of between subjects nature. And we're comparing a group of different individuals to a group of other different individuals. In a within subjects research design, it's distinct. We have the same people and we measure them before, and then we do something, and then we measure them after, right? So all participants are measured twice each individual receives both levels of the independent variable. And so whenever we have two measurements, right, when we're comparing two means within the same people, we use the correlated groups t-test. Now, one advantage of using a within subjects research design is that you have more statistical power, and you need fewer people in your sample to test the same effect that you would with a between subjects design. And the reason for this is because, in essence, people serve as their own controls and wash out the effect of individual differences. For example, a tall person before is going to be the same tall person after, right? So we don't really need to rely as much on random assignment in this situation. So going back, here's our correlated groups t-test equation, right? Where we're just comparing the difference between time 1 and time 2 over the same metric of error. The only distinction is that this is the standard deviation of the difference scores. And so here's a distribution of different scores. It approximates a normal distribution. And what we're attempting to do is, the null hypothesis would be that there's no difference between time 1 and time 2. And so we compare the difference that we obtain from our sample to a different score of 0. This is the same exact thing as comparing, as a one sample t-test, if we were to compare a sample mean to a population mean of 0. Okay, and so these more detailed formulas are most likely going to be very familiar to you, because in the last lecture we basically had the exact same formula. So in this top T equation, this is what you're going to use when you know sample means and sample standard deviations. And in the bottom, this is what you're going to use whenever you're just dealing with a raw data set. And so in addition, just as before, part of the T obtained equation involves computing the sum of squares. This time it's the sum of squares for the difference between the two measurements. And the calculation of the sum of squares incorporates squared differences and the sum of differences squared. So let's do an example. We will look at changes in heart rate among the 1988 National Aerobic Champions. So here's the full problem. A conspiracy theorist hypothesized that wearing leotards while engaging in aerobic exercise would have negative consequences on post-exercise heart rate. Specifically, he thought that leotards would absorb too much sweat, hold it next to the body, leading to a cool-down effect, which would reduce heart rate 5 minutes after aerobic exercise. To test his hypothesis, the conspiracy theorists collected heart rate data from 20 competitors in the 1988 National Aerobic Championships, all of whom sported their favorite leotards. He measured their heart rate 5 minutes before exercise, and then again following a 5-minute cool-down period after their competitive aerobic routines. While he theorized their heartbeats would decline after exercise, he was open to the possibility that his theory was incorrect. And it would be possible that the people would demonstrate increased heart rate after exercise. So he sought to test this hypothesis. Do the heart rates of aerobic champions change from pre to post aerobic exercise? Okay, so here, perfect example. He measured people at baseline, then they exercised, and then he measured them a second time 5 minutes after they exercised. So here we've collected sample data from the same people at 2 different points in time, right? Each participant received each level of the IV. So the independent variable would be time in this case. You could say before versus after, with before being the first level of the independent variable and after being the second level of the independent variable. And since there's only 2 means, we're going to use a correlated groups t-test. Okay. So, how do we do this? Well, first, we need to set up our hypotheses. So, let's look at how we've set up hypotheses in the past. Traditionally, we're comparing a mean or a population mean to a sample mean. And we say that the population, the mean of the sample is going to be equal to the population mean. And then for the alternative, we say that it's either going to be greater, less than, or not equal to, based on whether it's, a directional or non-directional test. However, with a correlated groups t-test, we're doing the same thing, but we need to conceptually reframe it. So essentially, what we're doing is we have 2 means, before and after, and if we subtract them from one another, right, the null hypothesis would be that there's no change, that the difference between before and after is 0. And so that's what we have here in this second example. The alternative would be that before minus after is either greater than, less than, or not equal to 0, right? So meaning that there is some kind of change. It could be higher, a decrease or an increase for a directional hypothesis, or not equal to 0 if it's a non-directional hypothesis. Now, moving down to this third example, this is probably the most concise way to report a correlated groups t-test hypothesis. So it just condenses it, and it says the mean of the difference between time 1 and time 2 is equal to 0. And for the alternative, the mean is either going to be greater than, less than, or not equal to. So let's think about what our null and alternative hypotheses are going to be in this context. So he was testing the hypothesis because he had a little bit of humility and anticipated that he could be incorrect. And so he wanted to examine whether or not there was a change in heart rate after exercise. So the null hypothesis is going to be mu of d bar is equal to 0. And the alternative, because he's just looking for a change, is going to be a non-directional test, which is mu of d bar is not equal to 0. And so we'll draw out our normal distribution here. And we say mu of d bar equals 0. And so if you noticed, there was not an alpha level reported in the problem. So whenever you encounter this, by default, the alpha level will always be 0.05 unless it's otherwise stated. So since this is a non-directional test, we're looking both above and below, we need to split that alpha level between the 2 tails. So we draw our line in the sand, which is what the t-crit value represents. And then we have 0.025 in this tail and 0.025 in this tail. And so beyond these lines here, this is our region of rejection. Okay. So now what we need to do is determine our critical value of t. And so let me move this over to the whiteboard. So here we can see that, over in this far left column, this represents the degrees of freedom for our test. So the degrees of freedom for a correlated groups t-test is n-1. So our experimenter had collected data on 20 people. That means his degrees of freedom is 19. So we go down to 19, and we want to find an alpha of 0.025 because this is a directional test. And we can see here an alpha of 0.025 in each tail with 19 degrees of freedom is 2.093. Okay. So T crit is equal to plus or minus 2.093. So this line here is going to be minus 2.093, and this line is going to be plus 2.093. Let me just get rid of that. Okay, and so now we need to set the decision rule for our hypothesis test. So the decision rule, same as before, is going to be reject the null if t obtained is greater than or equal to 2.093 or t obtained is less than or equal to minus 2.093. And you can see that maps on so that anytime our sample, the difference between our two sample means falls within the shaded region of rejection, we are going to reject the null hypothesis. And so for the next part, we're going to compute the obtained value of t. However, before we do that, we need to collect the data from the participants.
11 Prime movie, normally scheduled at this time, will not be seen tonight, so we can bring you the following special programs. Welcome to the 4th Annual Crystal Light National Aerobic Championship Finals, featuring regional finalists from all across the United States competing for the title of America's Best Aerobic Athlete.
We are the winners, watch us glimmer, like the sun for the champion. We're in control, body and soul. We push ourselves to the maximum. The champions, we are the champions.
Ladies and gentlemen, presenting the reigning 1987 Crystal Light National Aerobic Champions.
We take the spotlight. We are the ones, we're the champions. Working smarter, beating harder. We play to win, we're the champions. We're inspired, reaching higher.
Noah York, Terry Lilly, Eddie Stevens, Scott Cole, Jeff Vanderberg, Donna Davis.
The champions, the champions.
Introducing Introducing the 70 fittest aerobic athletes from across the USA competing for the gold in the mixed pairs competition. From the firm in Minneapolis, Susan Schwartzbauer and Doug Melrose. From the Ocean Bay Club in Pennsylvania, Lori Welteroth and Billy Ross. From Denver's Elite Sports Academy, Trish Hahn and Greg Corelli. From Move It In, California, Rosie Castaneda and Mick Stan Grover. From Gold's Gym in Los Angeles, Linda Bell and Mike Robinson. From Good Bodies in Dallas, Tiffany Oaks and Kevin Cregan. From All Sport in New York, Grace Mahalchik and Gregory Higgins. From Miami Hunt Club in Florida, Tanaj Milward and Jojo Vela. From Life Fitness in North Carolina, Nancy Harrell and Robert Kernodle. And from the San Francisco Bay Club, Deborah Casey and Andre Lully. In the teams competition, representing Valley Health and Racket in Orlando, Mama Hartnett, Debbie Harvey, and Marissa McKeechan.
Ain't nobody got time for that. Ain't nobody got time for that. Ain't nobody got time for that. Ain't nobody got time. Ain't nobody got time. Ain't nobody got time for that.
No, we certainly don't. We got to finish this t-test. So here's the data we collected, right? You can see on the left, we have the names of the athletes that we measured. And for each athlete, we collected their heart rate in beats per minute before they exercised and their heart rate in beats per minute after they exercised. And so this is our full set of raw data. And what we need to do next is we need to kind of fiddle with these numbers. We need to create a difference score. So this is a column where we compute the difference from before and after for each participant. And then after we compute those difference scores, we just sum them all up at the bottom. And then the next step is we're going to create a squared difference score for each participant and then compute the sum of the squared difference scores. So this is sum of squares. The only difference is we're just doing with using difference scores. So after this, then we need to compute our t obtained value. And to do that, first we need to compute the sum of squares for the difference. So the formula for SSD is SSD equals the sum of the differences squared minus the sum of differences squared divided by n. Okay, so let's compute this out. So SSD is going to be equal to 63550, and you can see that at the bottom in the rightmost column, minus negative 1106 squared divided by 20. Okay, and then that means SSD is equal to 63550 minus 61161.80. And this resolves down to 2388.20. So this is our sum of squared for the differences. And now we need to plug that sum of squares value into our t obtained equation. So t obtained is equal to d bar minus the population mean difference of 0 divided by the square root of our sum of squared score, 2388.20, divided by 20 times 19. Okay, and so this is going to give us 53, and then minus 0, but that, doesn't really do anything, divided by, or I'm sorry, not 53, 55.3. If you're wondering where I got 55.3, it's simply the mean of the differences, right? So you look at 11 minus 1106 divided by 20. Okay. So 55.3 divided by 6.2847. Okay, and so now we can resolve the final t obtained value is going to be minus 8.7991. That is a huge difference. So we need to go back now and we need to look at our decision rule. But before we do so, we should probably compute our effect size just for good measure. Some people would suggest that you should not report an effect size and you should check your decision rule first. I am personally of the persuasion that effect sizes should always be reported. So D is equal to T obtained divided by the square root of n. So you can think of this D value when you're trying to wrap your mind around what does this mean. You can think of it as the number of standard deviations that separates the means. And in this case, D would reflect the number of standard deviations that our difference is away from the population mean of 0, which means no difference. Okay, so D is going to be equal to negative 8.7991 divided by the square root of 20. So D is equal to minus 1.9675. Now, I'm aware your book suggests that you should report the absolute value of D, and that's perfectly fine. That's I think the way many people do it. However, the sign does convey a certain degree of information. It's the directionality of the difference. So either way you report it is fine by me. But let's compare this D value against, let's try to interpret it, right? And look at our little chart here on the slide. So this is a massive effect, right? So who would have thought, right, that doing exercise, leotard or not, doing exercise is going to increase your heart rate. So let's go back and let's determine if we reject or fail to reject our null hypothesis based on our decision rule. So let me scroll back up in the past of our whiteboard, and our decision rule is that we're going to reject the null if T obtained is greater than 2.093 or T obtained is less than minus 2.093. Our T obtained value completely blows that criterion out of the water at a T value of minus 8.7991. It's huge. So let's go ahead and write this up in APA style. Here is our APA style write-up. So as always, there's 3 parts to this. The first is what did you do? The second is what did you find? And the third is what does it mean? So for this first part, what did you do? Well, a correlated groups t-test was conducted to determine whether leotard-wearing aerobic exercise champions would demonstrate a change in heart rate after exercise relative to their heart rate before exercise. Heart rate data was collected 5 minutes before exercise and again 5 minutes after exercise. Okay, so the key thing here really is to just articulate what precisely you were comparing, right? And most importantly, that you're doing the appropriate test. Okay. So for the second part, what did you find? We say, compared to pre-leotard aerobic exercise, a mean of 8.45, the heart rate of aerobic champions after exercise, a mean of 135.75, was significantly increased. And then you report your t obtained value, which was negative 8.80. And by the way, in APA style, when you're reporting like a t or a standard error or a p value or a d value, you only go to 2 decimal points. And then you report the standard error of the mean, which is simply the denominator of your equation. And then p is less than 0.05. Now, if we did not reject the null hypothesis, p would be greater than 0.05. But since this was significant, meaning we provisionally will take on the alternative hypothesis, the probability that this result was obtained by a type 1 error or sampling error is less than 5%. And then we report our Cohen's d value, which was minus 1.97. Again, with or without the sign, I'm fine with that. And this is a large effect. Finally, what does it mean? Well, in contrast to initial expectations, there was not sufficient evidence to conclude that aerobic exercise while wearing a leotard would reduce post-exercise heart rate. Rather, aerobic athletes demonstrated large increases in heart rate following exercise, despite their leotards. Okay, and so here we have it all combined and written up as one write-up. And this is very similar to what you would see in a peer-reviewed scientific publication. And one of my goals is to help you be able to interpret what that research is saying by you knowing how to conduct these tests and write them up in APA style. So I really appreciate you playing today. If you like the video, again, please don't hesitate to like it and hit the notification bell. And also, please leave comments. If you have any questions or comments, leave them in the comment section below. I look forward to our next lecture, where we will be discussing confidence intervals, why they're important, how to compute them, and how to report them in APA style. Okay, thanks everyone. Have a good evening.